Greetings. My name's Chris. I am a graduate of Udacity's DA&D or Data Analyst Nano degree, as well as I've completed the first term of the Data Scientist Nano degree. And I actually work as a data scientist for a company in the retail and consumer analytics space. So for this mentorship application, I'd like to just do a lesson on a basic linear algebra and a refresher using NumPy, thinking that that will be very relevant for students in the DAN track. So I'm just going to pretend that the students have obviously have some familiarity with Python from the programming for data science course, but maybe not so much with NumPy, and maybe they could really benefit from thinking in terms of matrices, dimensions, vectors, and data types, because that will certainly be useful for getting fluent in pandas and later on for things like machine learning. Okay, so to begin, students, you should by now have Anaconda installed as your Python package manager, Conda rather, and you should already be familiar with using JupyterLab from the command line. In my case, you see that it says base and then Anaconda prompt. That's because I have confined Anaconda to its own environment, and it's not registered on the Windows path, and that's to avoid path conflicts with different installations of Python I have on my machine. Probably you can just do it from your regular command line, which if you're not aware of this, simply type the Windows key and CMD. Or in my case, Anna is enough to get it going. And hopefully you're following along with this notebook, which I will include as material at the bottom of the lesson. So to begin, we import NumPy. NumPy, as you may know, has some built-in and useful mathematical operators, functions like the absolute value function. And of course, we can abbreviate our imported packages for convenience of use. NP is canonical. And one of the reasons NP is so useful is because, like Python, well, Python is actually, as you may have heard, is built on top of C, compiled C modules. And NumPy is a Python package that exposes the code that you enter to compiled C underneath. So essentially, like if you declare a matrix in NumPy, that matrix gets converted into a C object under the hood, and computation gets performed in C, and then it gets converted back into a Python representation. And since C is a lower level language, much closer to the resources of a computer, the operations tend to be much faster, on the order of, I think, often 4 times faster or so, which when you're dealing with big data makes a huge difference between, say, 1 hour and 4 hours, 6 hours, 24 hours, and so on. So you may remember from high school math, and maybe even college linear algebra if you took it, matrices and vectors. So, you can represent a matrix kind of like this. You have row 1, column 1, row 1, column 2, row 1, column 1, row 1, column 2, row 2, column 2, and row 2, hopefully I can trim this out later. So, index position 0, 0, 0, 1, 1, 1, 1, 0, and 1, 1. And I'm calling it fake matrix because it's simply a list of lists representation. Whereas the NP matrix is properly a matrix as defined in NumPy. And NumPy has this nice sort of built-in pretty printing when you print out a matrix, which pretty print, if you're not familiar, is a core package for Python that allows you to very quickly print out things sort of element by element, or in this case, row by row. Like lists, NumPy matrices support indexed assignment. So here I'm replacing at position, row 0, column 0. There was a 1, but we replace it with 5. No, it works fine. But what happens if we try to overwrite it with a string? that would be perfectly fine with a list. But for a NumPy matrix, that is unacceptable, again, because underneath this NumPy layer, this matrix is a C object, and C objects require declaration of object type and allocation of memory. So that's one of the reasons it's so much faster. Everything is optimized. Memory is very strictly controlled. And string requires very different amount of memory allocated to represent it. Whereas ints are pretty, you have 8-bit integer, 16-bit integer, and so on. So if we just comment that out, it's fine. And to demonstrate that, if we take the matrix, NP matrix, dtype, we see that the default for an integer is integer 32. But we could have easily pretend that is something else, integer, say 8. And that's only because these are small numbers that works. And if you don't remember, the way bits or bytes work is, if it's 8-bit, that means you have this many possibilities. 256 values can be represented. And at least as integer values, right? But if we represent it as something larger, float 64, 64-bit float, that's a much, allows for greater precision, and 2 to the 64 possibilities, which is huge. Usually you're not going to need that unless you're dealing with large numbers. And you should get used to kind of thinking in terms of data types as you work with matrices, because you're going to want to optimize the values that are in the matrices to really help your computations run faster. Later on, you might encounter this with dealing with values from databases or from importing values from, say, pandas into a database, in which case the data type becomes very important. So this matrix has shape 2 by 2, which you can see, 2 rows, 2 columns. Here, you can, NumPy has pre-built zeros and ones, which churns out based on the dimensions that you pass, zeros of D type. You don't have to worry too much about D types in actual practice if you're just doing quick, demonstrative examples like this. Because when you actually do operations, like if I add these matrices, these 2 by 2 matrices together, it automatically gets coerced into float 64, which is necessary to accommodate the fact that this part is being added to the int 8 matrix of ones. So it kind of defaults to the larger, the more memory intensive D type in order to preserve as much information as possible, which makes good sense. You can, okay, we didn't cover addition, sorry, multiplication. So, so you may remember matrix multiplication, which requires that, you have, say, an m by n matrix, and you wish to multiply it by another matrix. Well, at least one of those axes has to be the same. So you can do, like, more concretely, say 5 times 10, and then multiply that by a matrix of size 10 times 5. Or you could reverse it, 5 times 10 times 5 times 5 times 10. But at least one of those axes must be equivalent in both matrices in order for this to be a valid operation. So here they're both 2 by 2 square matrices. This one of only ones, this one of only zeros. So we expect it to be zeros, and we get that. If you need a quick reminder of exactly what's happening here in terms of matrix multiplication, I'll give you a link to some useful materials in the instructor notes. So here we have taking our NP matrix, which had values 5, 2, 3, and 4. and we're reshaping it into single vectors. So what's happening here? So reshape just reshapes. This was a 2x2 matrix, but now it is a vector, a one-dimensional vector. You can tell because there's only a single list-like object here. If we want to make it into a one-dimensional matrix, then you need to have that 1 here to specify that there is another dimension, another axis. So here we have, a list within a list representation. So that tells us it's a two-dimensional matrix. And here we have a three-dimensional matrix. 5 rows, 1 column, one z column, so to speak, one z-axis. And in this case, we're calling the matrix multiplication function, which requires this, right? 4 by 1 times 1 by 4 matrices. We expect the output to be 4 by 4, and that's what we get. But when we go back to just simple vectors, all we're getting here is a pairwise multiplication. So 5 times 5, 2 times 2, 3 times 3, 4 times 4. So when you multiply vectors together, that's what you get. There's no matrix defined. There's no defined matrix multiplication for only vectors. So here are more element-wise operations, simple scalar addition and multiplication. And then here is the matrix multiplication again. Okay, now a note when dealing with matrices and matrices and, say, vector multiplication. So first we're going to instantiate a matrix called A. It's going to be random. I set a random seed so that the results will be, the randomly generated numbers between 0 and 9 here will be the same every time I run this, because a seed has been set. So there's our 4 by 4 matrix, matrix A. And now I also want to make a matrix B and C. This time, the 4 by 1 vector and then a 1 by 4 vector, both random. So essentially, this has the representation of being a column vector, and this has the representation of being a row vector. And you might be familiar with, the transpose operation. So matrix B dot T turns what was a sort of column vector into a row vector. Now instead of being 4 by 1, its shape, which you can check, is 1 by 4. And we can multiply by matrix multiply. So we're getting 1 by 4 by 1. We expect a 1 by 1 output. We get it. But how about the element-wise operator? So, we had matrix A, the 4 by 4 matrix. If we do element-wise operation, we're essentially just squaring every individual element, right? Which actually would be the same thing. No, not quite. Sorry. Okay. So that's, element-wise multiplication, which is well defined for matrices of the same size, same dimensions. But in this case, matrix B is 4 by 1, matrix C is 1 by 4, and yet the output is 4 by 4, which is weird because it should be element-wise, right? And in fact, if we were to make one of these transposed, it works just fine because now they're the same dimensions, so it's perfectly element-wise. So what NumPy does is something called matrix broadcasting, and it's a kind of interpolation. It does this by taking the second matrix and basically duplicating it to match the dimensions of the first matrix. matrix B. Matrix B was 4 by 1. So in order for matrix C to be able to do element-wise multiplication, it got replicated like this. So what happens is we get 7 times 5, 7 times 5, 8 times 5, and 1 times 5, all in this column right here. And then, everything here gets multiplied by the 9, forms this column, and so on. Sometimes this is a useful trick if you want to make sure that the output of your multiplication is going to be, say, a square matrix or just dimensions that you anticipate. And this is, again, just representing what happens when we have dimensional matching between our matrices. So that's just a very quick rush through of some important operations in NumPy. There's a ton more. I only have 15 minutes to cover things. So I've gone ahead and made some challenges for practice for anyone who'd like to try, just to get you more comfortable with thinking in terms of dimensions and matrix operations. And if you have any questions, of course, shoot me a line in the comments or you can message me directly. And yeah, thank you very much for your time. Happy learning. How do I stop this thing? Oh, there we go.